In the Khumbu area of Nepal, beneath Mount Everest, the temperature reaches -40 degrees Fahrenheit at an elevation of 10,000 feet. The atmosphere is sparse, making each inhalation insufficient. However, it's not just the cold that proves deadly. The wind intensifies it. This wind acts like an unyielding kinetic force, quickly removing heat from the body. This environment is ruled by harsh thermodynamic principles. Within this icy, mountainous desert, the Sherpa community has devised a way to survive. A classic Sherpa stone dwelling is more than a home, it's a survival mechanism. Each element has been perfected through hardship, and every feature is tuned to withstand a terrain that provides no inherent shelter. The issue isn't if a person can endure. It's about how a structure of rock and timber generates a tropical atmosphere when the external environment strives to freeze everything solid. Ascending the high Himalayas involves more than just climbing a peak. You step into a realm of extreme physics, where conditions above 26,000 feet force the body to adapt to a completely different set of biological rules. Beyond a point called the death zone, air pressure drops to under a third of what it is at sea level. This is not simply a shortage of oxygen. It's a critical deficiency in the pressure needed to push oxygen through lung membranes and into the blood. For those not acclimatized, this feels like gradual asphyxiation. Lacking the heavy atmospheric pressure typical at sea level, bodily systems start to fail. Fluid builds up in the lungs, high-altitude pulmonary edema, and the brain swells, high-altitude cerebral edema. Above this altitude, the body begins a fatal decline, breaking down faster than it can repair. Even in the lower year-round villages of the Khumbu region, at elevations between 13,000 and 17,000 feet, oxygen concentration is half of what is found in an average U.S. city. All physical tasks, carrying rocks, farming, or simply resting demand twice the exertion. This bodily strain is made worse by constant heat loss. As the sun sets behind Mount Everest's sharp ridges, the thermometer often falls to -40 degrees Fahrenheit. The 138-degree difference between body temperature and the outside air produces a severe thermal imbalance. The environment reacts to this difference with predatory speed, seeking to equalize it. The main tool of the Himalayas is convective cooling. Since there are no trees or thick plants to slow it, wind speeds up over the bare rock surfaces, causing a wind chill that makes the perceived temperature much lower than actual readings. At -40 degrees Fahrenheit, unprotected skin freezes within 2 minutes. The wind functions like a rapid heat exchanger, removing the thin, warm layer from both clothing and skin. Under such circumstances, staying alive without shelter isn't about willpower. It's mathematically impossible to withstand the deadly force of the Himalayan environment without Sherpa engineering. This approach avoids high-tech gadgets. Instead, it uses a clever passive design. It makes use of just 2 local resources, rock and timber. Here, the second law of thermodynamics poses a constant danger. The Sherpa home is built like a thermal stronghold. This dwelling views heat not as a product, but as a vital biological asset to be collected, saved, and protected. The design starts with harnessing sunlight. Above 13,000 feet, the air lacks density to retain warmth, yet it allows solar radiation to pass through easily. The Sherpas take advantage of this by positioning their houses carefully. In the Khumbu region, virtually every traditional home is situated on a southward-facing slope. This choice isn't driven by appearance. It's a crucial energy source. When the house's long axis is oriented to catch the southern sun, the entire building becomes a huge solar collector. In the brief winter days, intense high-altitude UV light hits the dark stone exterior, turning light into heat energy. Where fuel is hard to come by, the sun offers the first line of protection. It warms the outer shell of the dwelling before any internal heating systems begin working. Inside, the home is arranged according to a vertical temperature gradient. Traditional Sherpa houses are nearly always 2 stories high, a layout that tackles a key survival issue. The principle of ground heat absorption in the Everest region's near-Arctic climate means the earth steals heat. The soil is often permanently frozen, acting as a huge heat sink that pulls warmth from anything touching it. To counter this, the Sherpas place living spaces upstairs. The ground floor, called the bio, or chung sa, is set aside for animals like yaks and zoe. This is a clever biological design. An adult yak can exceed 1,000 pounds. It's a large, fur-covered heat generator with a fast metabolism. By keeping the herd downstairs, the Sherpas turn their livestock into a living heating system. The animal's body heat rises through gaps in the thick wooden floorboards. This provides a steady warmth level for the family above, so the living area floor never gets as cold as the frozen ground. The animals supply passive heat, while the family's actions upstairs generate active warmth. Yet the main protection comes from the walls. In a modern American house, we depend on insulation, light materials like fiberglass that block heat flow but have no significant mass. In the Himalayas, insulation alone won't work. You need heat storage capacity. Sherpa walls are built with a dual-layered method that matches medieval castle engineering. These walls are often 3 feet thick, made of 2 parallel rows of dense granite stone. The space between them isn't left empty. It's filled with a core of rubble. Earth and mud complete the fill. This creates a composite structure with 2 distinct roles. First, the earth-packed core acts as an air barrier, trapping air and blocking the fierce Himalayan winds from carrying heat away. Second, and even more important, the 3-foot-thick masonry works as a heat battery. This builds on the idea of thermal mass and heat lag. Granite is dense. A lot of energy is needed to raise its temperature. During daylight, when the southern sun hits the outside and the central fire burns inside, the massive stones soak up that heat. They don't become hot quickly. They absorb it slowly, like a sponge taking in water. After sunset, when outside temperatures plummet to -40 degrees Fahrenheit, the heat delay effect begins. The warmth stored deep in the 3-foot stone walls starts to move outward. Due to the masonry's thickness and density, it takes several hours for that energy to travel from the wall's center to the exterior. This creates a time lag when the outdoors is most frigid, typically between 2 a.m. and 5 a.m. The walls continue emitting the heat they stored 12 hours earlier. The house warms the indoor air again using accumulated energy. The wood in the structure also serves a structural function. In a region with earthquakes and strong winds, a solid stone building would eventually crack and collapse. The Sherpas incorporate heavy timber beams, often taken from lower valleys and carried up by hand, into the stone masonry. This builds a flexible framework that lets the house expand and contract during earthquakes or storms while preserving its heat retention. All aspects of the home are fine-tuned to cut down on energy waste. Windows are limited in number and size, mainly positioned on the southern facade to avoid the chimney effect, which lets heated air escape via the glass. Typically, the door is set low and offset to stop wind from rushing straight into the living area. Indoors, the main fireplace acts as the core of the system, yet the stone partitions and the animals underneath handle the bulk of the work. Building a fortress-like structure is not merely an engineering achievement. It exacts a severe toll on the bodies of humans and animals alike. The Solokhumbu region lacks roads, cranes, trucks, and any power tools. It operates as an economy without wheels. The landscape, a steep, jagged maze of granite and unstable scree, makes the wheel humanity's most fundamental innovation useless. Wheels need a level, prepped surface to work, yet the Himalayas provide nothing but steps. As a result, every pound used in a Sherpa house must be transported by pure physical effort. That's the reality of logistics. In its most basic and brutal version, constructing just one dwelling requires quarrying thousands of granite blocks, weighing several tons each. These slabs are shaped and carried for miles over hazardous paths where one wrong step can be deadly. The main mover is the human porter, employing a doko and a namlo. Porters handle burdens that break ergonomic norms by resting the strap atop their heads. This method shifts the load straight to the cervical vertebrae. This approach sidesteps the less powerful arm and shoulder muscles. It enables a single person to haul 110 to 155 pounds, often more than their own weight up steep inclines. This punishing work is sustained by the Sherpas' extraordinary glucose-fueled metabolism. For the bulkiest items, such as timber beams and base stones, they depend on the yak, the high-altitude world's living tractor. Evolution endowed the yak with enormous lung power and a heart built to push dense blood through a half-ton body. Its two-layer fur offers ideal insulation, letting it toil in snowstorms without a drop in internal temperature. Groups of yaks transport the heavy lumber required for the home's frame, plodding steadily and without pause through the high-altitude atmosphere. Across the Khumbu, the price of a house is counted in calories and distance traveled. Each stone stands for human exertion. Each beam represents animal stamina. The dwelling is small because every bit of its weight was won in battle against gravity. Without hydraulic lifts or reinforced concrete, the Sherpa builder has to be an expert in practical physics. Building in the Khumbu is all about using leverage, friction, and gravity, with no external energy source. These are the builder's main companions, a rock bar and a deep grasp of structural mechanics. To shift rocks heavier than the workers themselves, the Sherpa employs basic kinematic laws. Turning a terrain of unprocessed granite into an organized survival network involves shifting boulders weighing hundreds of pounds with exact force and leverage. A Sherpa builder sees a 500-pound granite slab not as something fixed, but as a weight that can be managed using the pick-and-pry technique. This is the classic lever principle. A steel rock bar and a smaller, steady stone act as the pivot point. The builder forms a basic machine by placing the fulcrum near the load to be moved. The builder optimizes the effort arm's length. This geometry lets one person apply a modest input force to raise a load many times their own weight. As one worker levers, another uses a pick to steer the rock or insert small wedges underneath, making sure each shift is gradual and steady. On a 4-5-degree incline, this gradual, cautious advance is the sole method to avoid a disastrous avalanche. For bulky, uneven stones that are hard to lift, builders use the penguin waddle. They wedge the rock bar under one edge to pinch and shift the load. They rotate the stone bit by bit around its center. For big, flat flagstones, the huge slabs for fireplaces or doorsteps, the builders walk the slabs. The slab is set upright on its edge, tipped onto one corner, then pivoted to the next in a corner-to-corner motion. The surface area touching the ground is greatly reduced, which minimizes friction. After materials arrive on site, the engineering focus transitions from kinematics to statics. In this system, traditional Sherpa walls are constructed using dry stacking. Their stability doesn't come from chemical binders such as cement, as those would inevitably crack and fail under the harsh freeze-thaw cycles in the Himalayas. The wall is instead held together by two forces, gravity and friction. The structure's integrity relies on how through stones or transverse bindings are positioned. These stones are long and heavy, extending the full width of the wall from inside to outside. They serve as anchors, securing the inner and outer masonry layers to each other. If these through stones were missing, the roof's weight would eventually make the two wall layers separate and bulge outward, resulting in complete structural collapse. After placing the primary face stones, the interior cavity gets filled with harding smaller stones and rubble packed with surgical precision. Correct harding evenly distributes the house's vertical load over the whole foundation, avoiding point loads that might break individual stones. For added stability, the walls are constructed with a slight inward tilt or batter, meaning the wall face leans a bit toward the center of the building. The builder uses gravity as a constant clamping force. Gravity draws the stones together instead of pulling them apart, which boosts the wall's ability to resist lateral wind pressure and soil movement. The last aspect of Sherpa engineering addresses the Himalayan region's tectonic instability. A rigid stone building becomes a death trap in an earthquake because it cannot dissipate energy and will break under tensile stress. To avoid that, Sherpa builders incorporate a flexible timber skeleton into the rigid masonry, a method called batar or timber lacing. This means embedding horizontal ladder-like timber frames at consistent vertical intervals inside the stone walls. These timber bands act like seismic belts, binding all four walls of the house together as one cohesive unit during an earthquake. The wood absorbs tensile stresses that dry stone cannot manage. The house can flex and move, dispersing the earthquake's energy via controlled friction from stones rubbing together and the wood's elasticity. In the most advanced fortresses, These timber beams are joined with dovetail joints. These interlocking joints are engineered to tighten when tension is applied, stopping the beams from separating during ground motion. Additionally, corner intersections are strengthened with horizontal timber pins that lock the beams in place. This design transforms the entire wooden framework into a cage that can sway without collapsing. The outcome is a hybrid structure. The stone delivers the thermal mass and compressive strength required to combat the cold, while the timber supplies the tensile strength and flexibility needed to withstand the Earth's movements. The Sherpas' stone houses are not merely shelters. They stand as proof of human adaptability. By merging biological evolution with advanced vernacular engineering like double wall insulation, the yak dung fuel cycle, and earthquake-resistant masonry, the Sherpa have transformed a death zone into a home. As tourism and modern materials, such as corrugated metal and solar panels, become part of the region, the fundamental principles of Sherpa architecture still emphasize the careful balance between thermal efficiency and cultural heritage.